In this section, we want to begin to put together the things that we've talked about regarding graphs of functions, whether the functions are increasing or decreasing, whether we have concavity, where we have maximums and minimums, where we have vertical asymptotes and horizontal asymptotes or slant asymptotes. We're going to put all of these things together to graph our functions without using a calculator. So one of the first things that we will need to look at when we have a function is what are the x and y intercepts. Remember, if we have an x-intercept, the y value is 0. So there's some x and y is 0. If we have a y-intercept, in this case, y is, x is 0, and we have some value of y. So in order to find an x-intercept, we set our equation equal to y, or equal to 0, excuse me. To find the other intercept, we set x equal to 0. So this gives us our x-intercept. This will give us our y-intercept. Another thing we want to look at is symmetry. We said that if we have an even function, that means that f of negative x equals f of x. This is an even function. It is symmetric to the y-axis. An example of that is y equals x squared. If all of your exponents are even, then you have an even function. If we have f of negative x, excuse me, let me take that off, and we get the opposite of f of x, we have an odd function, and we have symmetry with respect to the origin. Example of that is y equals x cubed. With an odd function, you will have only odd exponents and no constants. Okay, another thing that we want to consider when we are graphing is asymptotes, both vertical, horizontal, or slant. You will not have both a horizontal and slant. You would have one or the other. You might have a vertical asymptote, a horizontal asymptote, or a slant asymptote. We also want to consider where the function is increasing, where it's decreasing, and where we have extrema. And probably the very first thing, which I should have put as number 1, and I'll come back up here, is what is the domain of the function? We always want to consider what the domain of the function is. Of course, that also helps us when we're talking about vertical asymptotes. We need to consider concavity. So this would actually be number 6, concavity. And with concavity, where are our points of inflection, if any? So these are the things that we are going to look for when we begin to graph a function. All right, the first function we want to graph is y equals x over x minus 1. So if we consider domain, obviously in this case, x cannot be equal to 1. So our domain is all real numbers except for x. We could write it in interval notation, negative infinity to 1 and 1 to infinity. That is our domain. We want to think about symmetry. And if I were to plug in a negative x everywhere, That's not going to be the same thing I started out with, and it's also not the opposite, so there is no symmetry. Sometimes if you have symmetry, you can just think about one side of the graph and then be able to graph the other side because you have symmetry. If we want to think about intercepts, if I let x equal 0, we're going to get 0 over -1, which is 0. If I set y equal to 0, we still get 0, so our only intercept is the point 0, 0. If we think about asymptotes, there are no common factors that factor out, so here we have a vertical asymptote at x equals 1. Notice the degree of the numerator and denominator are the same, so we have a horizontal asymptote at y equals 1. To get increasing and decreasing intervals, we have to look for the derivative. So when we find the derivative, we have to use a quotient rule here. So the derivative is going to be the denominator times the derivative of the numerator minus the numerator times derivative of the denominator over the denominator squared. So this one is going to cancel nicely, and we get -1 over x minus 1 squared. No critical numbers. We have no critical numbers, but we still have to consider the intervals from -infinity to 1 and 1 to infinity because we have a break in the graph. But if we have no critical numbers, that means that we probably are not going to have any maximums and minimums either, because maximums and minimums can occur at endpoints and critical numbers. So let's just determine whether the graph of this function is increasing or decreasing. It looks like if I plug in f prime of 0, let me move this up just a little. We are going to get a negative value for the derivative, and then f prime of 2, it doesn't matter what I plug in, I'm going to get a negative value. So the function is decreasing on its domain. Okay, so we're getting some more information here. Now let's think about concavity. I'm going to move this up just a little bit more. In fact, let me go ahead and minimize it a little bit so we can still have access to some of our information. If we take the second derivative, well, this is the same over here as -1 times x minus 1 to the -2. So the second derivative is -2 times -1 over x minus 1 cubed. Wouldn't it be nice if they were always that easy? No possible points of inflection because there are no places where the second derivative equals to 0. But we still have to think about our intervals from -infinity to 1 and 1 to infinity. Second derivative, if I plug in a 0, is going to be negative. If I plug in a 2, it's going to be positive. So we are concave up from 1 to infinity and concave down from -infinity to 1. All right, let's see what we can do to put this function on a graph. We said that on this particular graph, we have intercept at 0, 0. I guess I could put some points on there. We said that there is a vertical asymptote at x equals 1 and a horizontal asymptote at y equals 1, so I'm just going to lightly graph those in there. And we have no maximums and minimums. We have no points of inflection, but we know from here that the function is always decreasing on its domain, but from negative infinity to 1, we are concave down. So it has to go through this point, so it's going to look like this. Decreasing on its domain, concave down. From 1 to infinity, it is decreasing on its domain, but it's concave up, so we're approaching asymptotes. And that is an example of the graph of y equals x over x minus 1. You can check it with your calculator if you want to. All right, here's another function. F of x equals 8 over 4 minus x squared. I'm going to rewrite this just because it's going to be a little bit easier to take the derivative this way, or I think it is. It's up to you when we get ready to take our derivative. When we think about domain, in this case, x cannot be plus or minus 2. If we set the denominator equal to 0 and solve, x cannot be plus or minus 2. That helps us when we go to look at our vertical asymptotes. If we want to think about symmetry, we are going to, because we have only even exponents, we know that this is an even function. Because if I plug in a negative x for x here where x squared is, I get the same function, so we're symmetrical to the y-axis. If we think about intercepts, if I let x equal to 0, my y is going to be 2. If I let y equal to 0, we get no intercept. So the only intercept that we have is 0, 2. If I let y equal 0, we'd have this. And 8 cannot equal to 0, so there is no y-intercept. Okay, we have vertical asymptotes at x equals plus or minus 2. And we have a horizontal asymptote at y equals 0. Degree of we have a constant in the numerator, so we know that the horizontal asymptote is y equals to 0. All right, for time's sake, I'm going to tell you that the first derivative turns out to be 16x over 4 minus x squared squared. So my critical number is x equals 0. So we have some intervals to check. I need to go from negative infinity to negative 2, where we know we have a break. Negative 2 to 0, 0 to 2, where we have another break, and then we're going from 2 to infinity. If we check the first derivative here, if I put the denominator is always positive. It doesn't matter what I put in the denominator, it's going to be positive. So if we plug in a negative number on top, the first derivative is less than 0, which means we are decreasing. If I plug in a -1 in the next interval, we're going to be, the first derivative is decreasing, is less than 0. If I plug in a 1, it's going to be positive. So we're increasing. That tells us because the derivative changes from negative to positive, we're going to have a relative, let's see, a relative min at the point 0, 2. And then if we plug in something greater than 2, it's going to be positive. Wait. Yes, positive. And so here we are increasing. If you will allow me, for time's sake, I will just tell you that the second derivative is 16 times 4 plus 3x squared over 4 minus x squared cubed. If I were there, we'd actually go over it, but you can figure that out for yourself. The second derivative cannot be 0, so there's no possible points of inflection, but we still need to check intervals. We're going to check from -infinity to -2, from -2 to 2, and from 2 to infinity. All right, now the denominator could change. The numerator will always be positive, so we only have to really worry about what we're putting in the denominator. So if I put in a anything that's less than -2, I'm going to get a negative number in the denominator. If I plug in a 0, it's going to be positive. We're plugging into the second derivative. And if I plug anything greater than 2, again, we are going to be less than 0. And so at this point, we are concave down, concave up, and concave down. So let's see what we can do to graph all of this information. Okay, so I've moved everything off to the side where I can still see it. I'm going to begin to graph what I can. I know that I have the point 0.02 is on the graph of this function. I have vertical asymptotes at x equals 2, x equals -2, and y equals 0. I know that my function is decreasing from -infinity to -2, and it's also concave down, so it has to approach the asymptotes. I know that in between -2 and 2, it's concave up, and it's decreasing until I get to x equals 0, and then it begins to increase, which that's a concave up. And then from 2 to infinity, we have an increasing function that's concave down, so it's going to look like this. So we just graphed that function by using all of the information that's been available to us. I think that's probably all that we're going to look at today. Your assignment, hang on just 1 minute. Your assignment is page 208. 1 through 6, 9, 10, 51 through 58.